Analytical means, right, mathematical. It doesn't have to be geometrical. We can use vector components. So the concept behind using vector components is if I have a vector A, which is pointing in the x direction, let's say it's a velocity which is 3 meters per second in the x direction, and I have a vector B, which is also pointing in the x direction, B equals 4 meters per second in the x direction. Those are two velocities. And let's say that vector A is the velocity of a fly relative to the air, and vector B is the velocity of the air relative to the ground. And I want to know how fast is the fly flying relative to the ground. Okay, let me say that again. If vector A is the velocity that a fly flies relative to the air, but the air moves relative to the ground, so it's pushing the fly along, then the fly flies at a faster velocity relative to the ground, which hopefully you can see is 7 meters per second. In order to figure that out, we had to add those two vectors. But we were able to add them easily because they're pointing in the same direction. Right? A plus B points in the same direction, so we can add them like scalars. The sum still points in the x direction, but because they're both pointing in the same direction, we could just add them up. How did I know I could do that? Well, just put them head to tail. Here's your vector of length 3. I'll leave off the units and direction. Here's your vector of length 4. And the sum of those two vectors points from the tail of the first, from the tail of the first to the head of the second. And the sum is, you should be able to see, the sum is just 7 meters per second in the x direction. What if the wind was blowing in the opposite direction? What if the fly is flying at 3 meters per second in this direction, but the wind is blowing at 4 meters per second in this direction? Well, we can still do a vector sum by putting them head to tail. Let's move them so the 4 meters, the tail of the 4 meters is at the head of the 3 meters, right? So here's my 3 meters. And let's move it so that the 4 meters, so they're head to tail, right? So this is, I should have drawn them in different colors, but this is the tail of 3, and this is the head of 3, and the tail of 4. Oh, I don't know if this is obvious. I think that's clear enough. I put them head to tail, the 3 and the 4, right? I put the tail of the 4 at the head of the 3. The sum goes from the tail of the first to the head of the second. Whoops, it's still not letting me do it. Okay, there we go. And so what's the sum? Assuming that they were meant to be parallel, they're not quite parallel. The sum, it turns out, now is 4 minus 3, or 1, right? So A, and we can write that as hold on. Sorry, I wasn't careful about my notation. Okay, I'm doing the second problem. So this is still vector A, and the wind, this is a different vector because it's pointing in the opposite direction. I'm going to call it C. So that A plus C is equal to the vector sum, which is you can see from the picture. I'm just trying to think of how to say this right. You can see from the picture is 1 meter per second in the minus x direction. What I was trying to show, or gonna show, or skipped somewhere was that C is just minus B, right? It's B in the opposite direction. So we can also say A plus negative B is equal to 1 meter per second in the negative x direction. A minus, or just A minus B. I wrote A plus negative B because negative B denotes that we're just turning the vector around. So A minus B is 1 meter per second. And so then you can see that's like saying A minus B is 3 in the x direction minus 4 in the x direction. So it's minus 1 in the x direction, or 1 meter per second in the minus x direction. I forgot to put my x hat. That's A minus B. The other thing is that you can put, again, I got to be really clear. You can put the minus sign here, or you can put the minus sign here. But you don't want to put it in both places if it doesn't belong in both places. Because, again, here's another aside. Minus 3 x hat is the same as 3 in the minus x hat direction, which is not the same as minus 3 in the minus x hat direction. because minus 3 in the minus x hat direction is, we can distribute those minus signs so in the same place and say that's plus 3. That's in the opposite direction of minus 3x hat. Okay, so here's an example, right? So again, this is just an aside of a place that I see a lot of people making mistakes. Here's what I'm trying to say. Let's say that you're doing a problem, and we define plus x to be to the right. And you find, as a result of the problem, that somebody displaces to the left, right? And you say, oh, okay, they displace to the left 1 mile. And so you say, oh, okay, that's in the minus x direction. So what you end up getting numerically is you get minus 1 mile in the x direction. But often what a student will want to say, or what somebody who's not paying attention will want to say, it's minus 1 mile. Oh, that is in the minus x direction. It's in the minus x direction. What you're trying to say, right, this is making the peanut butter and jelly sandwich incorrectly. What you're trying to say is, it's minus 1 mile. Oh, that means it's in the minus x direction. No. What that means, yeah, well, I mean, you are actually right. But what this means is minus 1 mile in the minus x direction is plus 1 mile in the plus x direction. What you really mean to be saying is that minus 1 mile in the x direction is the same as 1 mile in the minus x direction. That is correct. This is not equal to that. Okay. It's a common error to make. Is you say, oh, it's a negative quantity, so it must be in the negative x direction. But then you leave the negative out here when you also put it in here. And then you have double negatived. So let's go back to analytical sums. Analytical sums. So let's say instead the fly is flying. This is vector A, which was 3 meters per second, and that's our fly. But the wind is instead blowing south at 4 meters per second. The wind is blowing south at 4 meters per second. Now, some of you might know this geometry. I don't care about the geometry, but what is the velocity of the fly? The fly was flying to the east, and now the wind is blowing to the south. It's not blowing to the east or the west. I realized this was x and y, so we're not going to do east and west. Okay, so now this is 4 meters per second in the y direction. So which direction does the fly blow? The fly blows in this direction. And that's the resultant velocity right there. That's the resultant velocity. This is the resultant velocity. V resultant is equal to A plus B. Is it equal to 7? No. Is it equal to 1? No. What is it equal to? You can actually do the geometry of this right triangle to find that it is actually equal to 5 meters per second at some angle, which I haven't figured out, theta, below the plus x-axis, CW plus x. Okay. So how did I know that? I knew that because I know how to do geometry. But this is not what we're getting at right now. What we're getting at is that you can add parallel vectors, add like scalars. Otherwise, you got to do geometry. So the key here is that parallel vectors add like scalars. And if they're not parallel, they don't add like scalars. So we got to figure out how to add vectors that are not parallel. So again, for example, let's say I have a displacement vector in the y direction and then a second displacement vector in the y direction. The net displacement, those two add like scalars. But if I have a displacement vector in the y direction and then a displacement vector in the x direction, the net displacement, those two do not add like scalars. So we got to figure out now how to add these two, given this fact. We're going to use the fact that parallel vectors add like scalars. This is sort of a long statement, but I started writing it, so I finished. We will use the fact that parallel vectors add like scalars to turn all vector addition problems, regardless of the direction of the vectors, into addition of parallel vectors and the geometry of the right triangle.